If we change the equal sign to an inequality, then we can graph the inequality and solution. So we have some kind of a function, but instead of it being the regular function, so for instance, y equals f of x, now we have y is less than or equal to, or greater than or equal to. Or sorry, it was the other way around that I said it. We have a thing that we can graph. It's a relation, but it's a little more to it. It's not just a line. So let's consider this inequality here. Now we can simplify it, though we don't need to when we're graphing, because the Desmos or whatever graphing calculator you're going to use can handle it. But just simplifying it down, you can see that we can combine. We can split up the 5 to this, and then combine like terms here. We get this one. And now we have this statement here, and it's going to end up being a linear function. It's going to be a line, and this becomes a boundary line. And it's going to be just that line with the equal sign. Now, we draw a dashed line for this because of the strict inequality. If it was less than or equal to, then it would be a solid line. So just keep that in mind. This is what the line looks like, just to give you, just to show you what that is. So you can see that it's dashed here. Now, from this point, really what we have is we want to test a point on this graph, on one of the two sides of the line, to see if it's true or not. If you can test a point that's 0, 0, do so. It's always the easiest. But you want to test some points that are on something on this side of the line, something on this side of the line. So that's what we're going to do. We're going to test 0, 0, and 3, 0. 3, 0. Let me zoom in here, show you where that's at. You can see that 0, 0 is right here, and 3, 0 is here. Those are nice, easy points. If you can have 0 in there, that's going to make it much simpler for you. So testing 0, 0, we get 16 minus 8 times 0, less than 0. 8 times 0 is 0, 16 less than 0. This is false. Okay, let's test 3, 0. We get 16 minus 8 times 3, less than 0. 8 minus 3, or 8 times 3 is 24. And that is negative 8. And that is true. So you can see that the 0, 0 side of the line is false, and the 3, 0 side of the line is true. So we expect this region to be not true, but this region is true. And in fact, with Desmos, you can actually just type in less than y, and it will actually shade in the region for you, because all of these values on this side, all of these values here, make this equation true. And so this is our solution. This is our region of solutions. You can, of course, find a solution if you're to say y equal to 0 and solve this thing. What you would see is that you would see that it's going to end up being x greater than 2. That would be the interval you find, because that is x greater than 2 is all this stuff here, and that's the solution. That's, of course, if you make y equal to 0. We're not allowing y to be 0 here. We're allowing it to be a function. So it's two-dimensional, so we're going to have two-dimensional answers. So we get this whole side of the plane. Okay. Now, if here the boundary coordinates are not solutions, that's what we had. If we actually test 2, 0 into this thing, we're going to get 16 minus 8 times 2 less than 0. So we get 16 minus 16 less than 0. We get 0 less than 0. This, of course, is false. So that's the reason why the boundaries are not solutions. All you have to do though is change this to be less than or equal to, and then we have a solution, because if we test 2, 0, we get 16 minus 8 times 2, less than or equal to 0. Again, 16 minus 16, 0 is less than or equal to 0. Yes, that's a true statement. 0 is less than or equal to 0. And so what you would see is that that would change on this graph. We would end up changing this dotted line to a solid one. There you go. So that less than or equal to, change it to a solid line. As you can see, we have a solid line now. So that all the boundary points are now solutions. Okay, give it a try in number 3. So a system of linear inequalities that could also have equations in that system, but if you have one inequality, then it kind of changes it. This can really have a region of solutions. And just like I showed you, x being greater than 2, you have a whole region of solutions. This region, if it exists, this is called the feasible region. Now, it's found by finding all of the inequalities on a graph and then shading them all in, finding the correct sides and everything, and then finding all of the overlap. The overlap is the key thing to note. And in fact, the study of such systems for linear inequalities and equations, this is called linear programming. Actually has some roots in the, I think World War II is where it first came out. That's why it's called linear programming. And by using constraints, we find a feasible region, and a specific solution is what we're looking for. And what we want is it to maximize, to minimize or maximize some objective function. And this is typically a cost or a profit. That's what we're doing. So we use all of these constraints, and then we overlay, for instance, this objective function to find which point is actually the maximum or the minimum, depending on what we want to find. So, for instance, let's look at this problem here. We have a candy manufacturer wants to maximize profits, of course. That's what you're looking at. We have 2 types of box chocolate. So chocolate A gets $1.50 per box. Chocolate B is $2 per box. And these are the constraints that we're working with. We cannot exceed 1,200 boxes per month. And box B is no more than half the demand for box A. We also have that the production level of A should be less than or equal to, let me do a different color here. Let me just underline it. The production level of A should be less than or equal to 600 boxes plus 3 times the production level of B. So that's, of course, a kind of a weird constraint, but that's just what it is. So let's look at what kind of constraints we have when working with this system. So first off, we're trying to maximize profits, and we know the profits are $1.50 per box and for box A, and $2 per box B. So really, the question is, how much boxes should we produce? So I'm going to have 2 variables here. First off, we're going to say the x variable, I guess. We're going to need an x and a y, but really I'm going to leave it kind of as A and B. This is the number of boxes for chocolate A. And the y variable, which is going to be, I'm going to use B to kind of keep it more relative to what we're looking at. But we're going to need, once again, we're going to need x and y for graphing this. Is going to be the number of boxes for chocolate B. And with these two things, once again, I'm going to use A and B. So we know that we're going to produce at least 0 boxes. We can't produce negative boxes, right? That doesn't make sense. We also know that we're going to produce at least 0 boxes of box B. Now, we know that the combined production of both chocolates cannot exceed 1,200 boxes per month. So if we add the two together, this cannot exceed $1,200. That means it must be less than or equal to 1,200. The next part says the demand for box B is no more than half the demand for box A. So that the number of boxes we're going to produce for box B must be less than or equal to half of that of A, because it can't be more than that, right? The demand won't be for more than that, so there's no point in producing more than that. So we're going to make a constraint saying B must be less than or equal to half of A. And the final one says the production level of A should be less than or equal to 600 boxes plus 3 times production level of B. So production level of A should be less than or equal to 600 boxes plus 3 times the production of B. So this is our system of constraints. There's a lot of them here, but that's because we're constraining it down to be a single region. When we looked at systems of equations, we only needed 2 equations because we're looking for the intersection. Here we have a region of possible answers, so we need a bunch of constraints to find that. The last thing to note is that we're trying to have some kind of objective function, and the objective function is what we're trying to maximize or minimize, and this is we're trying to maximize the profit. So our objective function, I'm going to say z equals, is going to be the profit of these things. Well, we profit $1.50 per box of A and $2 per box of B. And we're trying to maximize this objective function. So this is our whole linear programming problem. We have all these constraints and this objective function. Now it's important to know that A is just x. So really we have x greater than or equal to 0, y greater than or equal to 0, x plus y less than or equal to 1,200, and so on and so forth. So that's what we're going to use to draw out this, this thing on a graph. X must be greater than or equal to 0. Y must be greater than or equal to 0. X plus y must be less than or equal to 1,200. We had y must be less than or equal to 1/2 x. And finally, this one says x must be less than or equal to 600 plus 3 times y. Again, I'm using x and y here, not a and b, because Desmos will not recognize a and b for the variables. That's the reason why we have to use this x and y portion. Now, of course, we have a lot of lines here, and it's a little confusing at what regions we're talking about. Well, we know from the first two, this is greater than 0 and this is greater than 0, so we must be in quadrant 1. It can't be anything else. It has to be here in quadrant 1. So let's actually turn those off. We don't really need those. Make it a little bit clearer what we're looking at. Now the next one says this one. We can see that from this one, this side of this blue line is shaded. So everything that's on this portion here, this triangle. Okay, and then in that triangle, we have the green says it has to be everything below this green line here. So everything in this triangle now. And finally, the purple says we must be above the purple line. So that means that we are everything in this polygon. Let me show that here. Okay, and I've created a little polygon here, and you can see that this is our feasible region. Let me turn off everything else. This is the region of all of the overlap. So our solution, the one that will maximize the profit function, or the objective function, I should say, which is this thing here, is going to be somewhere in this region. And the way we can look at that is by overlaying different levels of a profit function. Now, of course, the profit function here has three variables, z, a, b, which is also x and y, right? And this cannot be graphed on a two-dimensional system. It's got three dimensions, so it can't be graphed. However, we can graph different what are called contours. So I'm going to look at maximizing. I'm going to start with 0 profit and then go to maybe 100, then 200, and so on. And to graph all of those lines, and the line that gives me the most profit that intersects with this thing will be the biggest thing. Let me show you. Okay, so what I have here is I have the polygon here, and each one of these lines is a different contour function from the lowest z level. This is a profit of 0. You can see that because when x and y are 0 and 0, a and b are 0 and 0, we make 0 times 150 plus 2 times 0 is 0. So our maximum our profit is $0. So this is the lowest, and then each step is 100 profit. Let me just show you the actual code that I used. I created a list here going from 0 to 3,000, and then I plotted each one individually. 0 being this line here, and then it goes to 100, then 200, then 300, and so on and so forth. So what we want to do is find the highest line possible so that we can have the most profit. And following this thing up, the largest line possible is this one here. This one intersects with the polygon right at this point. And that will be our maximization of the profit. We could plug this vertex down here in, this one right here on the polygon, but that will not give us the maximum, right? This would actually give us more of a maximum, this point right here. And as we keep going, we're going to get bigger and bigger maximum profit to this one. And typically that's how linear programming problems work. The solution will always be on one of the vertices of the feasible region. So one of these corner points, and that really depends upon the shape and what you're looking for. Either you're minimizing or maximizing the stuff. So this is going to be our maximum right here at 800, 400. Let's go ahead and show that. We take z and equal to 1.5 times 800 was A, 400 was B. That's going to give us $2,000. Okay, and that's really how a linear programming problem works. Really, you can just test these vertices points. This one over here, let me turn off this for a moment. This one here is at 1050, 150. And so you could test that point into this objective function, but you're going to see it's going to be less than $2,000. So just test the vertices of these feasible region, and you'll find the maximum there. Okay, let's try it on another problem. We have a walkway of a bridge needs to be made of either spruce, which is 3 pounds each, or basswood planks, 4 pounds each, or some combination thereof. Now, the total weight must be between 600 and 900 pounds, and that's to satisfy a safety code. We have a cost of spruce being $325, and a cost of basswood being $375 for a plank. And we're asking what combination minimizes the cost of wood. That's, of course, what we want to find is the minimum. So we have two things that we need to know. the amount of planks needed of each type. So I'm going to say S, which I'm going to make that equal to X. This is going to be the number of spruce planks. And then Y, which is going to be, we're going to say B for basswood. This is going to be the number of basswood planks. Okay. Now, we know that it's going to be 3 pounds per spruce plank and 4 pounds per basswood. And the weight must be between 600 and 900 pounds. So really what we're saying here is that if we take 3 times S, that's going to be the total weight of the spruce planks, and add that to 4 times B, that's going to be the total weight of the basswood planks, this must be between 600 and 900 pounds. I think we can actually make that equal to, yeah, equal to. And the, well, we also know that, of course, S must be greater than or equal to 0, and B must be greater than or equal to 0. And actually, there's no other restraints on this system here, this situation. So this is our system. Of course, our objective function, the thing that we're really looking for, is going to be, we always typically use Z for the objective function. This is going to be the cost. So the cost is going to be $325 for spruce, so $325 per spruce wood plank, plus $375 per basswood plank, and we're trying to minimize this objective function. So with that in mind, let's go ahead and graph this thing and see what we get. So we have S was X, so X must be greater than or equal to 0, of course. And Y must be greater than or equal to 0. That really just means that it's in the first quadrant. And then finally, we have this 600 is less than or equal to, this may not be able to work in Desmos, let's just see, plus 4B. No, it's not liking that. So we're going to go ahead and just do, actually, let's try it again. No. We're going to have to do both individually. And then 3x plus 4y is less than or equal to 900. And so this is our system. Of course, we know we're in this first quadrant, so there's really no reason why to plot those 2 points. And in this region here, we have okay, everything greater than this blue line. So we're going to be talking about everything up here. And everything less than this green line. So everything down here. That means we're restricted to this one little band right here. Let me draw that as a polygon. Okay, there's our feasible region. And I can turn these things off. And here you can see it exactly. This is our feasible region right here. Now, our objective function was to minimize this thing. So let me go ahead and lay over our contour. All right, there's our contour. And once again, we're trying to minimize this function. So we're not trying to look for the one that's furthest this way. We're going to look for the one that's closest to 0 cost. And so the closest one, of course, is 1, 2, 3, 4, 5, 6, 7. So this is the furthest line out. That means we must be in this area here. And of course, you can see it must be this vertice there. That's the one that's closest to this line, the closest one in. So that's going to be our solution there, that vertice. And that vertice is at, let's see, 0, 150. So what that means is that if we only use basswood planks, then we're going to get to our safety condition faster, the 4 pounds each. So 150 basswood planks, 150 times 4 is 600. That gets us to the minimum, which of course that would be the cheapest way to do it, is go for the minimum. And even though it costs more for the basswood planks, the weight is heavier, so that it's much easier to get to that cost. So the minimized cost is going to be 0 150. Okay, that goes away, and then 150 times 375. That gives us $562.50. All right. Give this a try in number 4. Now, we only looked at 2 variable systems, as I say here, but in practice, really these linear programming problems can have such a large amount of variables and a large amount of constraints. There could be there's typically so many that you really need computers to help solve this. This was done by hand, but a computer can solve these things a lot quicker than we can. So that's what a normal linear programming problem is in the real world.